Hey everyone, today we will be going over graphs today, and without any further hesitation, let's get started. And now going over graphs. So graphs in particular are in a similar construct to our previous data structure we have talked about of trees, where trees are connected based on two entities, nodes, and branches as well. Well, meanwhile, graphs in particular are connected based on two entities, vertices, which hold our data point, and edges, which connect the vertices all together. And for us to be able to build out our graphs in particular, we use a tool in the STL library called vectors, where vectors in particular are much like in the case of a data structure that we have looked at before of an array or a list, except for the differences is that it is a dynamic type of tool that we use to be able to construct other complex data structures such as graphs and eventually binary search trees as well. We notice in particular for our vector that our vector is going to be comprised of a list of integers that we call ADJ for adjacency list to be able to build out our graph accordingly and be able to add edges, remove edges, perform depth first search, breadth first search, and we will also go in further depth of the different types of depth first search and breadth first search used for graphs for their different design techniques, both iterative and then eventually recursively as well. But focusing on graphs in particular, there are a multitude of different types of graphs, particularly directed, undirected, weighted, cyclic, acyclic, connected, and disconnected, where once we go further in depth inside of our practice problem, we will actually garner a further understanding to know exactly what these different graphs pertain to in particular. And in general, graphs have a time complexity of O of V plus E, where V represents the vertices and E represents the edges, where the more vertices and edges we have, meaning that the more complex a graph is, the greater the time complexity. And then the space complexity is going to be O of V for graphs, where V represents the vertices, and that means the more vertices that we have, the greater the space complexity as well, and the longer the time and therefore the longer time it would take and space required to be able to store your following program that you have made. And without any further hesitation, let's dive further in depth inside of our practice problem. And now going over our following problem. So our following problem states that we need to perform all of the following operations for our graphs. First, we need to add an edge between the two vertices. Then we need to remove a vertex and then remove an edge between two vertices. Then perform depth first search, both iteratively and then recursively, and then finally perform breadth first search, iteratively and then recursively for all of our graphs that we have over here for directed, undirected, weighted, unweighted, cyclic, acyclic, connected, and disconnected. And we will also have a custom GraphPrinter header file for each of the following graphs that we have accordingly. And without any further hesitation, let's head over and focus on our first problem, focusing on the directed graph.
And now we will be going over our directed graph, but prior to, I'm actually going to be first creating our header file to be able to print out all of the nature of our graphs that we will have.
And also a quick disclaimer, by the way, again, this chapter is up just to be able to not only get ourselves fully accustomed with the C++ syntax, but to also dive further depth in creating header files. You may feel free to be able to skip this chapter because the GitHub links are already in the description below. But again, this chapter is right here and it's great for practice for the following. So again, just putting it right here, putting it out here for the graph header file. This is also what it's going to be able to look like at the same time. Notice in particular about the outputs that we already have based on the picture. And without any further hesitation, let's go further in depth in our GraphPrinter header file.
I'm going to create a file called GraphPrinter. And this will allow us to see the nature of our entire graphs. So, first thing that we're going to be doing is that we're going to be including our libraries, our stream, and we're going to have 6 of these, 2, 3, 4, 5, 6, vector, list, cmath, string, unordered math, and also using namespace std. Then we're going to have our class called GraphPrinter, and a public instance that we have over here, and we're going to have 3 different instances. We are first going to print our graph, render our graph, and then draw our arrows accordingly. So in order for us to be able to print our graph, we're going to void print graph constant vector, as indicated by our adjacency list that we made earlier. List int and adjacency for a constant over here, and we're going to output graph adjacency list and endl, and for int v, indicating the vectors 0. V is less than adjacency list size, and it's going to continue up until we finally have our vertices here. Then we will output each vertices with a respective arrow, since we have an adjacency list that we are making to indicate the relationships between the two. And then we will use an iterator called it that's going to be equal to adjacency vector at the start, called adjacency v begin. Iterator doesn't equal adjacency v end, and we're going to still increment the iterator as well. Count it each space, and then we will have count and l, and then output here as well. And then we will output another format, graph edges using ASCII art, and L right here. Make sure all semicolons are attached. And we're going to render our graph by using this private function, private void render graph constant vector list int and adjacency for constant int radius equal 10, constant int diameter equal 2 times radius plus 1 with our vector of strings, since we are printing out our following graph lines, diameter string for diameter times 2, and then we will initialize our size that we have for the adjacency list, and we'll have an unordered map to indicate our positions with respect to the information we're getting from our adjacency list. Pair int positions. Then we'll have a for loop for int I is equal to 0, I is less than size, plus I. And then we'll have double angle equal 2.0 times pi from CMath, I divided by size, multiply that, and int x is equal to radius plus static cast int with radius times the cosine angle. Then we'll do the same thing for the y-axis, or int y for radius, but this time using sine angle, and then indicating for the position of I equal to what we have x and y accordingly in the inside. Then we will indicate with our vertices first initialized with respect to the size of the adjacency list, plus v auto x, y positions of v, and we will be dropping our graph lines using a vector at another point by using y x times 2 equal the initial point that we have. We just put this at 0, and then the graph lines indicating y with x times 2 plus 1, indicating the connection that we have initialized, and then plus vertices as well. Then while doing so with the graph lines, and we determine which graph line is which, of another for loop indicating for int v is equal to 0, and while it is still going through, checking our adjacency list, we will have our other vertex that we will be connecting that's outside of the adjacency list, which I will showcase in our directed graph and other graphs later. We'll draw the arrow, which will be a function called upon later, putting inside of our vectors, soon to be graph lines, positions of v, and positions of w as well. And then we'll have for constant auto and line, graph lines, count line, and outputting the line that we have for our graph. Then we will have our void draw arrow function as well. Put this right here. Yeah, it's already right there. So it's already set. Void draw arrow vector string and graph lines pair int from, and then pair int 2 for constant right here. Int x1 is equal to from first, and then y1 is equal to from dot second. Now we'll do the same thing for 2. X2 first, y2 second, and then we'll have other variables as well, indicating the position about where to draw the arrow. So we will have dx int s of x s of y, and then int error to know exactly what direction, because we are going to have the graph lines diagonal, straight, another diagonal up or left, right, in different areas. So we'll have the absolute value of x2 minus x1 with dy equal the absolute value of y2 minus y1, and then we'll have the instance of x1 less than x2 or 1 with respect to -1 over here. We'll do the same thing for y1 less than y2 or 1 with respect to -1 over here. Error dx minus dy. There we go. And while true, if x1 is be sure to equal x2 as an edge case, and y1 is equal to y2, we're going to break. Int error 2 equals error times 2 if e2 is greater than -dy. We'll have error less than decremented with the distance of y, and then x1 goes up with respect to x, s of x. And then we'll have the other edge case of e2 less than distance of x, with the error of incremented for the distance of x. This is to indicate the exact position of where the arrow is going to be drawn, so sy with respect, and then if x of 1 doesn't equal x of 2, or y of 1 doesn't equal y of 2, we're going to have graph lines indicated as y positions of y1 with respect to x1 times 2, and we will set this one to be straight, indicating if we have something that is directly connected, since we were putting our formats in a circular fashion. But again, there are different variations of graphs that we would have, but that would be cyclical in that case. But again, we're just showcasing in particular just the natures of graphs and how they're connected. And then graph lines y2 x2 times 2 with respect to the following arrow as well. And so, just want to be sure we got everything. And the reason being is because we don't have a main function yet, so that's what I'm going to be indicating over here. Return 0. Let's just build this, make sure, and it succeeded. All right, and also for reference as well, I have the following header file at the same time already inside of the GitHub repositories in the description below. So again, this would be our printer file that we'll be using to be able to actually print out our following graphs as well. And without further ado, let's head over to our directed graph to be able to build and showcase.
And now going over our direct graph. So, part 2, what we will usually be doing is that we're going to be including our libraries, which should be the following. I'm going to have 3, 4, 5, 6 libraries to include as well. So I'm going to go include iOS stream, include vectors, I'm going to include a stack, include a queue, I'm going to include a list, I'm going to include algorithm, and we're going to include our header file. And also, just a note, our GraphPrinter header file is applicable to 6 of the graphs are already listed in here. Again, the descriptions already contain the GitHub link, so you can look at the README to see in particular on where the GraphPrinter actually applies in this case. So we know exactly where it's being printed, and the only different variations that we have are going to be inside of the on the weighted graph, and then we will have the undirected graph. Those are really the big 2 graphs that have those different modifications. But again, just for disclaimer and just letting everyone know. And then finally, what we'll be doing is that we will have using namespace std as well. And then what we will be doing is that we are going to have our class over here. I'm going to call this directed graph. And I'm going to have a public instance over here. We are going to initialize our variables by number of vertices by int v over here, and then we'll have an adjacency list of, you guessed it, a vector list int. I'm going to call this adjacent, and then we're going to have our constructor that we're going to call, which will be directed graph int v over v here. Then adjacency list resize, so that way we could be able to call upon it based on the vectors that we're actually putting inside of it as a parameter. Just be sure to put the semicolon. Yep. Okay. Then the next part, I'm going to be focusing on adding an edge. Then going over the question, remove a directed edge from vertex v to vertex w, since we are dealing with 2 vertices, because in order to have a graph you need 2 vertices along with an edge. And then we will move a directed vertex and all its associated edges. Then we are going to perform depth first search iteratively, starting from vertex v, and then perform DFS recursively. Then we will do the same thing for breadth first search as well. Search, breadth first search. And then all we're doing right now, since we're going to be focusing on the first part of adding an edge, what I will be doing, and this is going to be insanely easy, all we need to do is have this function, void add edge, that we call int v and then int w, since in order to have a graph you need 2 vertices along with an edge, and then all you have to do is that inside of our list of vectors that we're going to have, we're going to push back at it in context with W. So this is how we connect two vertices with an edge accordingly. And now I'm going to be able to test this thing out to make sure that we have everything already set up in place, and also be able to print out the necessary graph as well. So we're going to have directed graph. We're going to call this graph with 6 vertices altogether. So you have 0, 1, 2, 3, 4, 5, and then graph dot add edge. Based on the function that we have, we need 2, so I'm going to have 0, 1, and I'm going to put in the other ones, and this is how we are going to connect. 2, 3, 4, 5, 6. So that means we're going to need 1 and 2, 2 and 3, 3 and 4, 4 and 5, 5 and 0. So now I'm going to build this to make sure that we are good. Alright, and it's already set up in place. And also I'm going to call upon GraphPrinter, and I'm going to call this printer as well. And that means just with that, all we need to do is just print out print graph based on the following vector. So we have graph.adjacency list that we made from our vector. And I'll put the semicolon over here. So let me just build this. Build succeeded. We're going to run this. And it showcases our graph already. And we have the graph adjacency list, so that way we know exactly what is already connected. So based on, let me just zoom over here. So after we have added the following edges, this is what our graph is going to look like. We notice in our graph adjacency list we have 0, 1, 1, 2, 2, 3, 3, 4, 4, 5, 5, 0. And the following graph we have for our directed graph, notice the arrows and the constant direction that we have. That's indicated that is a directed graph. And it's also in a circular fashion, which means it's cyclical, and a non-circular fashion means acyclical, just for further context as well. And so, yes, this was adding an edge for our directed graph. Now we will be focusing now on removing a directed edge and a vertex as well, based on the next 2 problems that we have. So we can do this either way, but again, I'm just putting the removes next to each other in particular. That's the next step that we will be doing. And now focusing on removing a vertex and an edge. Really, I'm just going to be focusing on removing a vertex. Actually, we'll just focus on removing an edge first for the sake of convenience. So, or you know what, I'll just go in order right here. Remove a vertex and all its associated edges. We're going to be doing this function void remove vertex int v in particular. And while we are scanning through our adjacency list, auto and neighbors, adjacency neighbors dot remove these specific vertex from the adjacency list, and then we're going to clear all edges from the vertex. We do adjacency with v. We're going to do clear. Function called in from the STL library for vectors, namely, and this is what makes it really convenient. There we go. So it's just this entire function that we have, and so we are going to go into our main function, and then we're going to see in particular on removing a specific edge. Oh, sorry, vertex. So. And it's really going to be easy, so we're going to have graph.remove vertex, and let's just go with 3 in this case. We're going to output graph after removing vertex 3. and down. Printer, print graph adjacency over here, as we already removed the following vertex that we have. And I'm just going to be printing this out. Let's build this, make sure it's all good. Build succeeded. I'm going to run this bad boy, and this is what the graph looks like really when we remove our vertex that we have already set in place. This is a disconnected graph at the same time from the following, and we will be practicing a little bit more to actually build out the full graph so we can get fully accustomed with the C++ syntax. But yes, one can see the differences from what we already did from adding our vertices and edges and then removing a specific vertex as well from our graph. And so yes, this was removing a vertex as well. Now let's focus on removing an edge. I'll just put this right here. That would be the next step. And now we're going to be removing an edge from two vertices, because in order to make a graph you need two vertices and an edge to connect together in order to be able to make said graph. So what I'm going to be doing, I am going to be able to create a function called void remove edge, and we're going to put inside our two vertices inside. So we're going to have int v, int w, and then all we are going to do is that we are going to be using a function inside of the vector STL library called remove. And then we can remove w as well, based on our adjacency list of vertices we have, and w as well. And then we're going to go straight inside of our main. We're going to remove an edge by doing the following. We're going to go graph, remove edge, and I'm going to say, let's go with 4 and 5. So 4 and then 5. And then we're going to output the following right here. Graph removed updated graph with 4, 5, edge removed, and then we're going to print the updated graph as well. There we go. Let's run this, make sure it's all good. It succeeded, and look at that. So that edge that we have made is completely removed from 4 and 5, and this is still more of a disconnected graph as well. So yes, this was removing an edge, as we have already stated over here, and now we will be performing depth first search iteratively for our directed graph. And now we're going to perform depth first search iteratively, so I'm going to go void depth first search iterative for our following vector that we have over here, and then we're going to have a vector of Boolean to determine if what has been visited as well. Visited v for false, and then we're going to, since depth first search typically uses stacks, we're going to create a stack of integers to indicate what has already been visited, and then we're going to push any vertex that we have to start inside of our stack. And while the stack is not empty, we're going to take the top of the stack. I'm going to consistently add it by doing a stack pop, and then see in particular what has been visited and such. So if the following vertex has not been visited from what we've already been added, we're going to output the following vertex as well, and the next one at the same time. And then we're going to go visited for v equals true, indicating of what has been visited. There we go. Then we're going to have a for auto loop as well. So for auto I equals adjacency list of vectors plus our begin, starting at the very beginning, which, given the fact that a stack typically operates like a stack of plates where everything is considered at the top, this is why we have our begin. And then the next part we're going to go as I as an iterator doesn't equal adjacency v end over here. We're going to increment I accordingly, and then we're going to check to see what has been visited and what hasn't by saying if the following iterator sees a vertex and has not been visited. By doing this symbol here, we're going to keep pushing inside of our stack until we have seen everything already. Okay. There we go, and then I'm going to put count and L. And now the next part, I'm going to go directly back inside of our main function, and then we can do iterative depth first search. In fact, I'm going to put this right here prior to us removing everything. There we go. Count depth of search, iterative, starting from the first vertex, which is what we see. And then I'm going to do graph.depth of search, iterative for the very first one, which will be 0. Make sure you have your semicolons here, and then we're going to run this. Build succeeded, going up the top. Yes. All right. So after the graph has already been built, in fact, what I'm going to be doing, I'll just put this up here to be able to showcase what has been going on. There we go. This should probably give us, there we go, depth of search. Right here we see 0, 1, 2, 3, 4, and 5. And this is the process for us to be able to actually have depth of search iteratively for us designing it. So again, this is how we perform depth of search in an iterative stance. And there are different ways that we could actually build depth of search, such as recursion by calling upon depth of search repeatedly as well. And that'll be another design pattern to be able to put in that I'll be showcasing to you folks to actually show the nature of depth of search and how it's typically built in different formats. So yes, now let's focus on building depth of search recursively. And now we're going to perform depth of search recursively. So the way we're going to go about depth of search recursively is that we're going to build 2 functions. One being a helper function. And we're still going to get the same results, just the order and the way how we're actually building out depth of search for us to be able to understand recursion and the principles behind it. This is what we do in particular. So I'm going to have our helper function. Actually, let me just indent this just for the sake of notes. So helper function is going to be void depth of search recursive int v with the following vector of boolean. And visited, and if it's visited for a following vertices, we're going to indicate true. In this case, we're going to output each vertex that we have visited like we did before with iterative approach, and then we're going to have a for auto loop for auto I is equal to a dj for vector at the beginning, and then we'll have I if I doesn't equal the vectors adjacent, the vector inside the adjacency list at the end, then we're going to keep incrementing I until we actually reach the end. And if the iterator has not visited a particular vertex, then we're just going to call upon depth of search recursively. Notice in particular how we're looping through in this. This is the magic behind recursion. You're able to call upon the function in and of itself to loop around, saves a bunch in particular on actually building it out, which is why it's widely popular. And then we're going to perform depth of search recursively from vertex v. Now, all we need to do, since we have our helper function, what we're going to be doing, void depth of search recursive start. I'm going to call this int v. And all we need to do, after we have our vector boolean to indicate what has been visited for a following vertex that we are calling from at the top, and then we're going to first initialize by using false. Then we're going to call upon our helper function, put it inside, and indicate for a vertex that has been visited to initialize. And then we are going to keep printing this out until we have reached the end. So it's just calling upon this function to go inside and just keep going. That is the principle of recursion. There we go. And now I'm going to head straight into the main function and iterative, recursive. So we're going to output depth of search recursive, starting from the first vertex, which will be 0 in this case. And then I'm going to perform graph.dfs recursive start, calling upon from what we have already made. That's going to call upon our helper function. Let me just showcase. Yeah, so it's going to call this function right here to then call this function and perform recursively, starting at the very first vertex, which we have as 0 in that case. And then it's going to output with what we have. Build succeeded. Let's go back to the top. There we go. It does perform the exact same thing that we have, similar to the iterative approach. It's just the way we built it out is just a different format. Now you can do different variations. This is iterative, and this is recursive that we have to start between the two. Let me just, there we go. So that way we can see everything. Let me just zoom out a little bit. There we go. So that's iterative at the top over here, and this is recursive. We have right there, and this is depth first search recursion. And we see the differences between the two overall. Now let's go to breadth first search, focusing on iterative and then recursive. And now we will perform breadth first search iteratively. So the way we're going to go about this is much like in the cases of what we have done similarly for depth first search, except for differences. As you guessed it, breadth first searches use a queue, which is why we included it in the library that we have. Depth first search always uses a stack, breadth first search uses a queue. And so we're going to go down and we're going to create this function void breadth first search iterative, indicating the first vertex that we put inside. And we're going to have a vector of booleans indicating what has been visited, and then call upon our integer that we have initialized at the top for v, and then we are going to have false, indicating that we have not visited anything yet. And then we're going to create a queue, and remember, queues operate by first in, first out, which is very important because what we have done for our for auto loop, our begin, because stacks operate like a stack of plates, where we have the most recent at the top, and then the very first entity already at the bottom. And they operate based on, stacks operate based on LIFO, queues operate based on FIFO, first in, first out. Apologies on that. And we'll have iterative integers called q, and then we'll indicate what it has been visited. For v, indicating what's true. And then we are going to push each vertex that we have visited inside, and then while the queue is not empty, v will indicate the queue at the front, and then we are going to output each vertex that we have, and then queue pop, and then we're going to have this for auto loop like we have over here. Auto I for iterator, adjacency v at the start, then iterator doesn't equal the adjacency list that we haven't visited at the end. We're going to just keep going through with our iterator to indicate what has been visited. If it is not visited, indicate I over here, then visited. For I equals true, q.push for iterative I. And then finally we're going to output at the end sorry about that. And then what we'll be doing is that we're going inside our main function to breadth first search iterative, and the way we're going to be going about this is we will be outputting breadth first search iterative starting at the very first vertex. So I would do graph dot breadth first search iterative at the very start, which will be 0, like in the case of what we did over here. Breadth first search iterative already, and now we're going to run this. Build succeeded, looking at the top, and it does the exact same thing that we did for depth first search for the following output. It's just a different nature of how we are actually collecting each of the vertices and then outputting them accordingly. And so yes, this was breadth first search, and without any further hesitation, let's head over to recursive breadth first search. And now we're going to perform breadth first search recursively. So similar to what we have done already for depth first search, we're going to have two functions. We're going to have our helper function, and then we are going to have our actual function we will call in the main function. So similar to what we did before up here, except for what we're going to be doing is that we're going to call this void. Yeah, I'll just put right here, void breadth first search recursive And since breadth first search uses Q, we use Q integers and Q, and then we'll have a vector of a Boolean vector indicating what has been visited. And then if the Q is empty, we're just going to return as a base case indicating, hey, there's nothing in the queue. And we're going to indicate for our first vertex to be at the front, since queues operate by first in, first out. Then we're going to pop the queue to be able to output our vectors, vertices as well, and for each vector accordingly, similar to what we have done there. Indicate a space. We'll have a for auto loop. For auto, I is equal to adjacency vector at the start. Notice, like we did over here for a vector inside of our depth first search recursion for each iterator. We're gonna have begin, and then while the iterator is not at the end, we're going to increment our iterator accordingly, and if the iterator has not visited a vertex inside of our adjacency list, we're going to have visited, I'm just going to call this right here just to avoid misspelling, I indicated as true, and then we're going to push each iterator accordingly. And then we will perform breadth first search recursive. This is where the definition of recursion actually comes in, and then indicated what has been visited as before. So we are putting in the same parameters as we have already done thus far. And then we will put in our actual function that's going to call upon the helper function and just go through accordingly. Breadth first search recursive start int v for vector Boolean vector indicating what has been visited with our vertex that we have initialized at the top over here. And indicated as false, saying we have not visited, and then q integer of q visited each vertex for true. And then we're going to push each vertex accordingly inside of our queue, and then we will do, sorry about that, breadth first search recursive, there we go, indicate for queue, and then visited as well, and count and L. So we're calling upon this function that we have for a helper function, and then yeah, so that's recursive breadth first search right here. Now we're just going to do what we did before, recursive depth first search, and then recursive breadth first search recursive, and all we got to do, we're calling upon this function at the start, similar to how we named it before for depth first search start. We're going to go over here, perform breadth first search, and we are going to give this similar output. It's just the way of how we designed it. Alright, the build has succeeded. Let's go to the top, and yes, it has actually performed the following breadth first search and depth first search accordingly, giving the similar output. It's just a nature between how we are actually building out breadth first search and depth first search iteratively and then recursively as well. And so yes, this was our direct graph and how we actually perform breadth first search recursively, and this is the full context for our directed graph on outputting each part whenever we have the following tasks. And now we will head over and focus on our undirected, and then we will focus on our undirected graph for our next iteration as well. So yeah, let's just move forward.
Hey everyone, thank you very much for taking time to watch this. If you found this video helpful, be sure and feel free to please like and subscribe. And if you do have any other questions or suggestions, please put them in the comment section. And as always, take care. Cheers. Bye-bye.